Hey Ramblers, this video covers chapter 1.6 in our textbook, or actually just the first half of 1.6, and we deal with two really closely related functions. As we try to develop our library of functions, important components will be power functions and polynomial functions. Now we'll talk a little bit about how power functions are sometimes confused with exponential functions, and then we'll talk about a little bit how power functions compare to exponentials, and how they're really not that similar, and how exponential functions really grow a lot faster than power functions. Then we'll move on and talk about polynomial functions and how they are related to power functions, very closely in fact. Okay, Ramblers, please pause often, take good notes, and thanks for watching.
Okay, let's start off with the definition of a power function and make sure we don't confuse it with exponentials. So a power function comes in this form: f of x equals some coefficient k times x raised to the p. So k is just a coefficient, like, we could have something like 3x squared. That would be an example of a power function. Our exponent is a number we know, the base is the variable, and the coefficient is any old number. Other examples of a power function would be 1/2 x to the 5th, or maybe even negative 8 x to the 7th. But in each case, the exponent is a positive integer, it's not a variable, the base is our variable, and the coefficients are any old number. They can be positive, negative, you name it. But as long as the exponents are positive whole numbers and the base is the variable, you have a power function. Okay, now let's take a look at what these things look like. Power functions come in two main varieties. We have odd power functions and even power functions. Now that is very analogous to the discussion of symmetry. Odd power functions are going to have an odd exponent, and they are going to be symmetrical about the origin. You'll notice that as the exponent gets larger, they grow faster. So x to the 5th is going to grow more quickly. I'm sorry, that was x to the 3rd. X to the 5th is going to grow more quickly than x to the 3rd. Now let's talk about even functions. Even functions have an even exponent, and they look more parabolic. So x squared is that familiar parabola, and as the exponent gets larger, they get a little wider at the base, but closer to the closer to the y-axis. In other words, the parabola gets thinner as x gets, as the exponent gets larger. Okay, let's take a look at how power functions compare to exponentials. Now, exponential functions grow quite rapidly. In fact, it's almost in our vernacular that when something's growing exponential, we know that it's getting very large. But if we look at these three frames, you can see that that's not really the case when you're close to 0, or I should say when x is close to 0. Because when x is close to 0, x cubed dominates 2 to the x. So the power function is dominating the exponential function. But as we look at our next frame, you can see that as x is getting bigger, and not much bigger, as we look at x out to, say, 15, and y up to 2,000, we can already see that the exponential is going to cross the power function and begin to dominate it. So that when we finally get out to a really zoomed out window, where we're looking from x from 0 out to 15, but y is now 10 to the 4th, which is like 10,000, you can see that the growth of 2 to the x is practically vertically, and y equals x cubed is in fact kind of growing quite leisurely in comparison. So the important note to take away is that exponentials dominate power functions. In fact, exponentials dominate everything. And this brings up the term end behavior. The book is going to use this in the exercises, and it really is a good idea to start getting familiar with it because limits are coming up. End behavior is just the behavior of the function as x approaches infinity or as x approaches negative infinity. So in other words, what's going on with the function as x gets really big or really negative? Let me leave it at that. In this case, exponential functions dominate power functions as x gets larger and larger. Okay, let's move on now to polynomial functions. Polynomial functions are really closely related to to power functions. They're really just a sum of power functions. And they, of course, have non-negative integers, just as the power functions did. So we see different kinds. We have the quadratic power function, where the lead term has an exponent of 2, a cubic, where lead term has an exponent of 3, quartic, and then quintic. Now, you could go on and on. You could have n equals 6, you could have n equals 20, you could have n equals any number. The largest exponent for a polynomial can be anything. But notice, unlike power functions, which really only had the two general shapes of like a seat or a parabola, polynomials have these bumps in them. And you'll notice, as we start to go through these things, that the number of bumps is one less than the lead term. So a quadratic, where n is 2, has just one bump. A cubic has 2, a quartic has 3, and then a quintic has 1, 2, 3, 4. So they will have at most one less than the largest exponent. Okay, that's important. What gives these bumps? Well, we started out with power functions, very simple. How come a cubic has these bumps in it? Why isn't it just like a seat? And how come this quartic isn't just a plain old U? Well, I'm sure you've already guessed, it's these other terms. The lead term gives it the general shape, but these other secondary terms kind of give the bumps on the inside. Let's take a look at how that happens, and you'll see that when you're zoomed in, the bumps are quite apparent, but as we zoom out, it's not the case. Let's take a look at the next slide. Okay, I want you to pause the video for a minute, and you can just keep this screen there as you do some work on your calculator. I want you to graph two functions, y equals x to the fourth in y1, and y equals x to the fourth minus 15x squared minus 15x, over two different windows. The first window is going to be, x is going to be between negative 4 and 4, and y is going to be between negative 100 and positive 100. That'll be our first window. The second window is going to be a little larger for x. X is going to be between negative 20 and positive 20, but y is going to, we'll keep the lower bound of y the same, but the upper bound of y is going to be up to 200,000. Be sure to set your y scale at an appropriate level. I would say set it at 20,000 so that you don't have too thick of an axis to be looking at. Please do that and make some observations between the two graphs that you see. Okay, you should have seen something like this, that when we're looking close up at the two, the picture looks very similar to the top here. We see that y equals x to the fourth. That power function is just our parabola, a little bit wider than x squared, but looks very similar. Whereas the second function, x to the fourth minus 15x squared minus 15x, has these bumps in it. Those bumps are caused by subtracting the 15x squared and the 15x. But as we zoom out, the power functions, the two power functions, quite frankly, are indistinguishable. But this second polynomial function looks almost identical to the power function. And that is an example of end behavior. As x gets toward infinity, or as x goes to negative infinity, and in this case, x didn't have to change that much. We're just talking about from negative 20 to positive 20. You can see that the power, the lead term, dominates this, this function, that even though we have all this stuff hanging on to x to the fourth in the polynomial function, it still looks like a power function. So when we talk about end behavior, What we're really referring to is what's going on as x gets large, and as you can see, the end behavior of a polynomial is that it just equals the lead term power function. Okay, let's move on. Okay, let's talk real quickly about how we find the formula for a polynomial function. And it's really not all that difficult. There's a couple things we want to pay attention to. So imagine we were given this graph here, where we can see that the curve has an x-intercept of -3, a curve of 1, an intercept of 1, and an x-intercept of 2. And we notice that the y-intercept is -12. And if I wanted to find the value for the function, I'd know that it would equal f of x times each of these roots. We'd have x plus 3, x minus 1, and x minus 2. We'd also put a k in front just because these lobes or these dips can be deeper or higher depending on the value of a coefficient. Remember, it's that coefficient in front that stretches vertically or shrinks a function vertically. So we need to know what x is. All right, well, how do we find x? Well, that's where the y-intercept comes in. Since I know that -12 equals k times all of these factors, I can plug in 0 for x. And when I do, I can solve for k. And there you can see that k equals -2. So the final form of this is f of x equals -2 times x plus 3 times x minus 1 times x minus 2. All right, let's take a look at one more example involving something called double roots. Okay, double root occurs when a function intercepts the x-axis but does not cross it. So here we have a function, and since we can see that it has, well, let's assume that it only has these two dips. I know that it crosses at x minus 3. So f of x equals k times x plus 3. And then it does not cross at 2. It has a double root at 2. So we're going to say that's x minus 2. And double roots, when they don't cross, we write them twice. So that would be how we represent the double root, as this x minus 2 showing up twice. We can't, in this case, solve for x because we don't know what that y-intercept is. If we did, we could go ahead and solve for it, but without it, we just have to be comfortable that this equals some k times the two roots x plus 3 and x minus 2 used twice. Okay, Ramblers, I hope you took good notes. Pause if you need to, and thanks for watching.